Yeah, yeah. Understood, understood. Yeah, I was just asking because if it's time to create a self-contained model for clock, like you said,
Mhm.
I think that's a crucial part, right? You cannot do that with discretized models.
No, but so basically our model is discretized. It's the only way, like kind of we kind of escape completely, kind of like, or staying operational in the sense that we can kind of also measure the behavior of our clocks, is to assume this kind of continuous background time. If this makes sense, but otherwise our model is completely kind of discrete in the sense that all energy states are kind of discrete energy states, and kind of the ticks, kind of the signal you get from this clock comes in discrete packages. Um, but yes, there's definitely kind of a tension uh, with that, how people look at time measurement. I
Paul,
hope that makes
for you,
sense. Yes.
in your statement that you just said, what is background time? Can you define that for us, please?
So this is basically like it's kind of local back. I would say like even Schrödinger time or local background time is basically kind of this the parameter under which kind of quantum systems evolve. So like given kind of the behavior of a system, which is modeled by a mathematical object called the Hamiltonian, if you let kind of this evolution of a quantum system run for a certain time, then you get to a different state, and kind of this time you let it run, that's what I would call kind of background time, or but it's something that's local, in at least in quantum mechanics. And then a lot of yeah, problems, or like not so much with special relativity of, but as soon as you combine it with general relativity, then problems arise.
So, in terms of quantum states that you just mentioned,
Hmm.
is it kind of a simultaneous state, which you're considering a quantum state?
Uh, no, quantum state is, in this sense, I just took kind of a mathematical object. It kind of lives in a complex Hilbert, like a complex vector space, uh, instead of kind of a real one as classical variables do. And there's
Got it.
kind of a subtle differences in the description. And you have like you can do more stuff, and it seems that kind of on a very kind of small scale, actually nature acts this way. Like it shows phenomena as such as entanglement and yes.
Thank you for saying the word entanglement. Alexander, your turn, sir. Thank you.
No, no, thank you. I just want to say I thank you for joining us today, Paul. I really appreciate that. You didn't have to do that, so I just want to say that. And Zach, you're on stage. If you have any questions, please feel free. It's an open conversation.
Okay, I'll keep that in mind. Thank you. I'll just take on a few for a moment.
So, Paul, it just the last word that you said is entanglement, right?
Hmm.
So, in terms of quantum entanglement, can you explain to us just for the room's purpose? And I know what quantum entanglement means, but can you just, in your own terms, define quantum entanglement and how it relates to time, essentially?
I don't know how it relates to time, but I don't like you can like there's different kind of way, like there's ways. I would just say what it is for me first. Like it's basically like kind of the possibility of systems to share an overall global state. So it can have, for example, two parts or two systems, and instead of like even like each one being in a well-defined state, they can have an overall kind of well-defined state, while kind of having individually very kind of undefined, like not undefined, but very kind of like being in the most entropic state, which is basically that all out. If you kind of interrogate the system, then it will give you each outcome kind of basically randomly with a 50-50 chance. Um, so yes, this for me is quantum entanglement, or like kind of the basis. And how it relates to time is it's something that we still don't know. In a sense, there's kind of this there's like a paper from the 80s was written by Page and Wooters, so that's two physicists from the US, and they basically showed that kind of uh, you could kind of use this phenomena of having an overall well-defined or like kind of definite state uh, to kind of show that you could kind of, if you sit on one side of this, of like two entangled systems, of like one of an entangled system, and you look onto the other, you see an evolution, although you have like a static overall state. So it's kind of something like a uh, and this was kind of like, it was kind of forgotten for a long time, and it kind of resurfaced or gained popularity the last years, and people did a lot of kind of research in this direction, and kind of now use it as a formalism, which they call Page-Wooters formalism. And yes, but it did not lead. It did lead to a lot of nice technical insights, and people generalized these things. But I think so far there's no kind of actual kind of experimental or things we can draw from this so far. Yes.
Paul, what's the name of the theory called again?
The two guys are Page,
Uh-huh.
and the other guy is Wooter. So that's Wootters.
Got it. Page
That's one.
Wooters.
Genau. Yes, and you will see like there's like, it was written in '83, and there's like very funny, like also a little bit annoying, because they basically present this very nice result that works for two particles, and then they just add a paragraph where they say it's easily generalizable to like arbitrarily many particles, but it's actually a hard problem. And they also never wrote after this on the same topic, but people actually like 30 years afterwards managed to kind of derive nice results in this direction.
Got it.
They
Thank you
just,
so much.
yes.
Paul, so you mentioned that can you repeat the part where you said that when you stand and look back, there was a deformation? Can you rephrase? Can you repeat that?
Okay, so basically the basic result of Page and Wooters, what they show is that you could kind of like have like an overall static state, which basically is kind of a time invariant global state of systems. But if you kind of look on a kind of local and marginal perspective, if you stand on one kind of part of this overall static state and you look onto the other one, then you actually see something like change or evolution.
Okay. So Paul, wow, thanks for saying that. I
Yes.
think so after speaking to you today, I have to say I'm even more confident in my formalization of intelligence. I've been working on this for quite some time, and everything you've said today has been in line with what I've sort of come to learn. And my formalization is very simple. It's actually symbolic. And because my formalization is so abstract and symbolic, it actually gives me the ability to derive essentially all other an infinite amount of models from this one abstraction, which I think is sort of the foundation of intelligence, and that time is actually an emergent phenomena. And since it's discrete and it's emergent, what are the rules that governs the emergence of time, the interaction of time, and the evolution of time? And when you said that when you stand on one of those variables and you look back at the other two variables, you see an evolution, you see a change. You know, when I stand on, if you envision a triangle, an infinity, and a circle, and imagine that these are three-dimensional objects, and then imagine that you're standing within the circle like a Vitruvian man, like Da Vinci drew the Vitruvian man. And now imagine that behind the circle is the infinity, and beyond that is a triangle. So when you stand at that door as the Vitruvian man, what you're seeing is the evolution of time all the way to the end until it converts into a triangle. So when you were speaking, that's how I visualize it, and it's all in line with the symbolic representation that I formalized. That it's pinned up on the in the room up here. So thanks for joining us
Okay.
today, Paul. Really
Okay.
appreciate it.
Yeah, I'll try to have a look. I just like one thing kind of that guides me, or like I don't know, like it's just a personal thing, but that also a problem that I have with string theory. Like the more models you have, like for example, string theory, kind of I think now it gives you like it encompasses everything, because it's basically kind of the the mathematical model that kind of includes all models of all physical theories that we know. So it basically has everything. But then it leads to the problem that you actually kind of don't find any correspondence to kind of the real observable world anymore, because you have like so many models that you don't have any kind of way to pick one that you would say that we kind of that corresponds to the one that we live in. And the only way you can kind of do this then is like need to use the kind of anthropic, or like the kind of anthropocentric kind of principle, where it's just okay, we live in the one that we live in, but it kind of loses explanatory power. So yeah,
Exactly,
I don't
Paul.
know. I will have to have a look. But
Yeah.
as far as I kind of say this, like I think it's very good people like kind of use their imagination and kind of visualize things, because sometimes kind of this advances us in a lot of fields, like people that kind of visualize things that other people don't see. Uh, but also I would say like the more general a model gets, like the less kind of explanatory it kind of, there's kind of this trade-off in the same sense that we have with like maybe that's the wall that
Paul,
we run
exactly,
into
Paul.
with this
Language,
yes,
Paul. You just said it. Language,
yes,
like literally, language is one of the barriers. So if we are to formalize anything at the fundamental level, we have to go beyond. We have to transcend language. And that's my issue with a lot of the mathematical formulations, is that they're nice and discreet and beautiful in a way, but they're still sort of incomplete because it's math, right? And
yes, but it's
the
the most
language of
powerful
math is incomplete.
language we have. Like it includes all other languages that we know.
So can I quickly come in?
Yeah, jump in, Joel.
Right. Um, talking about language, I do agree with both of you. I do agree to some extent with Alexander, with the incompleteness theorem that is trying to bring into this discussion, and how that comes in with language, you know. But I also think that some of the answers to that, Paul have some of the answers to that. So Paul mentioned a statement that when it comes to like all, he made a statement regarding all observed phenomena in physical reality or in nature seem to have dis- seem to be discrete systems. Seems to suggest that nature is discrete. Is discrete. So my question is, I would like Paul to expand on that, and I will. And the thing is, there can be a discrete system that also have no. There can be. I mean, there it is both discrete and indiscrete systems or infinite system can both be simultaneously true, and that kind of logic system is an infinite logic system itself, or is a non-deterministic logic system. It's a logic system in which two contradicting truths can be simultaneously be true, and that type of logic system is an emergent of the quantum mechanics or quantum mathematics. So I would want Paul to go into that statement he made, and how Alexander's dimensional complexity and algorithmic efficiencies actually come into that.
Okay, so I'll just say that I have to leave in 10 minutes, but I'm happy to kind of try to kind of rephrase, or like kind of give this statement again. It was actually not about the nature of things; it was rather about kind of how we can observe them, and that basically the only way we can observe nature is through kind of discrete values. Like we're not able to perceive continuous values, or like we cannot measure continuous values. I would not even know how to save values that are continuous. And of course, like there's no contradiction, like, or what says contradiction, it depends on how far you go away. Like if you kind of look into a screen, it kind of seems continuous, but like the kind of closer you get, like the more discrete it gets, until you arrive at the pixel. And so this kind of, like, there's also things in between, like quasi continuous systems, which are maybe like seem yes. On the other hand, like to this language thing, like, yes, like I think like language is inherently like limiting us through the incompleteness theorem and stuff. And but at least as far as I know, like mathematics, or like as far I can judge, mathematics is like the most powerful language we have. It includes all other languages, and is kind of the best way to express stuff without ambiguity, and also communicate to other people kind of models or kind of assumptions about the world without ambiguity. Yes, and I don't know, like maybe you what you kind of want to look in, if you kind of want to kind of go a little bit further than kind of the normal math is, like go from set theory to category theory, and then maybe you you find some nice stuff there, because I think that's kind of the like the most general, most powerful language, if you want to have like very general statements that we have.
You mentioned a statement right there saying that the smaller you go, the more things become as if they're discretized. So
Yes.
are you suggesting that at some point, if it turns the limit of how small you go to zero, space-time could be discretized?
Probably no. Like we have kind of values for length and time scales for which we know kind of that we cannot say anything beyond or smaller than this, which are basically like the Planck length and the Planck time, uh, for which is so small that we like far off of kind of going anywhere near them in our observations. Um, but these are kind of the, like these values are kind of the smallest thing we kind of can resolve in theory. And yes, like so far it kind of, this was the case, no, like we kind of thought atoms, or like as kind of science, we thought atoms were kind of the smallest thing we can see, and then we could look into them and we found like other kind of discrete things that kind of made up an atom. And uh, maybe I don't know, I'm not a big fan of string theory, so I don't think there will be strings, but like maybe we can at some point look further and find like different objects,
Okay.
uh, maybe even continuous ones, who knows.
So if
I
space and
don't know at the present moment.
I just want to add to what you just said. If space and
Mhm.
time is if when it comes to observation, okay, I heard someone ask a question about observer, the agent, and a system, and we resolve that to saying the agent itself is an observer, and the agent, and the system, the agent and the observer is basically indiscriminate. You cannot differentiate them. So the agent is equals to the observer, and then the only thing is it boils down to the agent and the observer. So the agent, which is the observer, and the information. So if you look at things from that perspective and say that, okay, if possibly, okay, the more you tend to zero, the ever possible possible observation that you can ever make is it tends to discretize space-time. Doesn't that mean that there's a chance that, or that isn't that equivalent to saying that the universe is computational in nature? If you look at the fact that you just said that as it tends to the smallest space-time scale, you are discretizing space-time, and therefore looking at the universe from an entropic perspective. And when you're looking at the universe from an entropic perspective, you're also looking at computational phenomena.
Um, yes, that I don't know. I think what you were kind of or like what maybe was included in your statement is basically the church-Turing hypothesis, no? Which is basically a statement about kind of by Church and Turing, which they said basically only stuff that is efficiently computable by a Turing machine actually also kind of exists in nature, expresses itself, loosely formulated. Yes, but
Yeah, you don't have to.
yes.
I was happy whenever when it was opening. Yeah, go ahead. Sorry.
Wait, Zach wanted to say something, I think. Is it me or?
Yeah, definitely. Okay, so I had a few thoughts. First of all, about the intelligence portion. To me, intelligence probably kind of falls under the sort of setting of like set theoretic topology. So I feel like mathematics sort of is much more broad than just set theoretic topology would be. Um, Mathematics, I think, is a subset of logic. I don't know how in depth it can actually be like scrutinized in the future, but um, and also about the regards to the I'm not sure. I've not heard anyone really say it before, but my view is that there is not a universe as a sense of like everything belonging to one collection, as much as there may be a universal object, and the rest of us are just kind of reflections across that. So that's everything I wanted to say. Thanks.
Is that can you elaborate on that, please?
Yeah, the reflection point.
Yeah.
Yeah, so my idea is that essentially there's a universal object which exists, and everything else is
Okay.
basically open
Wait.
to.
How do you define this
Yeah,
mathematically? What's the dimensionality of it?
yeah, I don't. Well, I actually have an idea what it could be. There's a if you look at a brick wall, you can put numbers onto a brick wall with a certain formula, and you essentially get numbers that it kind of how do I put this? You basically you take a brick wall, you pick a triangle, or you pick a brick on there, and you can make bigger and bigger triangles, and you can encode a formula that places numbers across every single like bricks, every single brick. And I developed this myself, so I don't know what the dimensionality of it would be, but my idea is that it's basically like a numerical. It would kind of be a computational, I guess, to a degree, but everything else would be a some kind of like there'd basically be I don't know how there's some between it, but I just don't see the idea that we all exist in the same universe. So it just seems kind of like an old idea to me, but that's just my thoughts.
No, I like how you think, Zach. Actually, I like how you think. Oh wow, interesting.
Mhm. Before leave, or maybe like Zach,
Before you leave,
if you're not
Paul.
yes, if you're not, just one comment to Zach, if you don't like the limitations of set theory, go to category theory.
Paul.
It might help.
What here
Yes,
is that?
category theory.
Okay, for Paul, I have a question. Okay, when you talked about time, okay, from my own understanding of time is basically due to change in the system. And when you come to my own understanding of building a clock is therefore looking at the changes in the system in which you're using to build a clock, knowing that you have a predicted amount of changes or a predicted cycle of changes over time. You can then use your prediction or expectation and compare it to the current change, and then use that to state or to extrapolate what the time currently is. So my question with quantum systems is my question with quantum systems is it seems as though the quantum systems in general is confused, meaning that is confused of the forward time or the backward direction of time. Basically, in a quantum system, does not know the forward arrow or backward arrow by itself, but the way it actually measures that, or we as humans um, 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 extract the forward arrow and backward arrow of time is the idea of the quantum memory, where the memory itself and looking at the entropy, entropy helps us to know what the forward arrow of time is versus what the backward arrows of time is, according to the second law of thermodynamics, which is the fact that the entropy of the universe is always increasing. So Michael, I'm having a question that how does a subset of how does a subset in the universe, which is a